All right. So lesson 7F. What are we doing today? All right. What we're doing is we're using radians to simplify math calculations that, when done in degrees, get real tedious. Okay. And really, I'm trying to get you to understand is the connection between radians and calculus. Okay. You've heard me say at least 100 times that doing calculus in degrees is difficult, if not impossible, and that you must do radians in order to really understand where a lot of the connection lies. Okay, so that's what we're going to do today. Is we're just going to dive into further analysis using radians. All right, but before we do that, I want to go back and I want to revisit something that we did in 8th grade. Okay, with the 30, 60, 90 triangle. Part of the reason why trigonometry is difficult is because of our deep-seated understanding of degrees, or rather our lack of understanding. Okay, so I need you all to imagine that you're back in geometry class and you're seeing a 30, 60, 90 triangle for the first time. If your teacher said that the smallest side is opposite the smallest angle and that side length was 1, what was your natural intuition, or what do you think most 8th or 9th graders would say about the side opposite the 60 degree? How long do you think they say that side would be? They would say 2. And why do you suppose they say that side is 2? Because 60 is double of 30. Okay, now, we know that's not correct. Yes? What should 2 actually be? Root 3. Okay, but then the follow-up question is why? Where are geometry students in 8th and 9th grade, where are they living when they go, well, 30 is to 1 as 60 is to 2? What are they thinking of? It's a math word that has a P, starts with a P. They're thinking of proportions, but in particular, a linear proportion. So part of the challenge about teaching trigonometry only from the aspect of ratios is that we're completely missing the circle, right? So there's really, when we see this, we intuitively know, well, why is that middle side length root 3? Well, it's not a one-to-one connection between a rotation, right? Really what's going on here is that there's a circle out there, right? And that 30 degrees is the rotation from point A to point A prime, yes? Okay? And so we're trying to move out of that world and we're trying to get into the world of radians. So the issue is there a direct connection between degrees, which were what? Degrees were arbitrarily chosen by the Sumerians and Babylonians 4,000 or 5,000 years ago because they had a hexadecimal number system. They counted by 60s. They just divided the whole circle up into 360 parts. Yes? It was an arbitrary number. They thought that may perhaps have been the length of a year. It wasn't because of an attribute associated with the circle. Okay, so then fast forward a couple hundred years, or somebody somewhere comes along and says, well, there's got to be a better way. Okay, there's got to be a better way, and that better way is radians. Yes? So when we measure circles, what is the ratio of the circumference of any circle to the diameter? What does that yield? Doesn't matter if the circle is the size of the earth or the circle is 1 inch diameter on my piece of graph paper. If I took the ratio, the circumference to the diameter, what's that going to yield? It's a transcendental number, probably it's pi. Okay? It's pi. The circumference is what? That's the distance around the circle. That's the length of the arc, is it not? That is the complete arc length of one full rotation, yes? What is the d? How can I restate d? 2r. 2r. Let me get rid of that. It's 2r. So can I connect radius, which is a linear measurement, to my curvature, which is the what? Circumference. So pi is that connection. So that is why we use radians. Okay, so let me show you something real quick here. When you get to calculus, the first part of calculus, you're going to spend the better part of a whole month learning what the derivatives of various functions are. Now, the derivative is simply the slope of a curve, because calculus came out of nonlinear math. The question was, how do I calculate the slope of a curve? Okay, so what you see right here, this is the graph of the sine function if I use degrees on the x-axis. Is there any semblance of a curve there? No. So I've got, it's not perfect, but the x-axis is the same scale as the y-axis. So if you look, it's almost a box, 20 on the x, 20 on the y. When I have the same scale using degrees, I don't see the true relationship. But if I use radians, what happens? Yeah, I get the curve, right? Now remember, pi is how much? 3.14. So when I'm right here, if you look at the sine curve, 0 is the x-axis. What is my angle of rotation where my x-coordinate is 0? I'm sorry. I said x-coordinate. Beg your pardon. This is the sine. I meant to say y. Where is your y-coordinate 0? Pi. And pi is 3.14. So when you look at this graph right here, 3.14 is where 0 is at. Okay? So I can use a graph where the x scale is the same as the y scale and things make sense and I can see the relationships. Okay? You cannot do standard analysis on degrees. It has to be in radians. So next year, you're not going to see degrees at all. Everything's going to be radians, okay? So what we're doing today is I'm trying to get you in the habit of getting out of degree land into radian land. Do we get that? Yeah. Okay, great. All right, so now let's go back to your notes. Where are the notes? Here we go. All right, so if you recall, when you were in geometry, you had to calculate portions of circles, whether it be the portion of an arc length or what we call sector area, which is just a portion of the overall area. And we had to use degrees. So we always had these unfortunate scale factors in here, right? Yes? So length was some proportion of the entire circumference. I beg your pardon, my writing. Circumference. Your area was some proportion of the total area, okay? Those are not very convenient formulas. But if we use dimensional analysis, you've probably heard that term in physics and chemistry. If we use dimensional analysis, we can greatly simplify the matter by basically converting from degrees to radians. So my arc length, we used to use theta over 360 degrees, but how many degrees is 2 pi radians? 360. So we can get out of degree land and get into radian land by multiplying by 360 over 2 pi, right? That gets rid of my degrees and puts me in radians, right? And then I simply use the circumference 2 pi r as before. But what happens to my 2 pi in the denominator here? It's going to cancel with the 2 pi in the numerator, and it's going to leave me with the length of an arc in radians is just the rotation times the radius. So much simpler than before. Okay? So let's do the same thing, the same type of dimensional analysis with area. Area used to be theta over 360 degrees times pi r squared, but now we're going to convert, get out of degrees land, move into radian land, and then we're going to look at what happens. My 360s cancel, pi cancels, and it leaves me with area equals 1/2 theta r squared. Does everybody see that? Okay, much more elegant and streamlined than the prior formulas. Okay? So this little tidbit here is simply reiterating what we went over a couple minutes ago as far as the importance of radians to calculus. Okay? So let's jump down here and do some examples real quick because I'm almost out of time. Okay? All right, example 2. A satellite is in circular orbit 200 miles above the Earth's surface. By the way, all these notes are posted. Okay, we took up a lot of time earlier today going over the homework and the quiz and doing the quiz. Okay, this homework is not due next class. I'm moving the assignment out because of all the time we spent earlier today. Okay, so we will finish. Yes, you're welcome. We will finish these notes next class. Okay, after you take the quiz. Yes. Okay. All right. Example 2. A satellite is in circular orbit. All right. So what do we do with this stuff? Circular orbit, 200 miles above the Earth's surface. All right. So we've got Mother Earth here, the big blue dot, and then we've got some satellite, rotating out here in space, and that radius is going to be the radius of the Earth plus 200, right? Does that make sense? Okay. So assuming the Earth's radius is 3,956 miles, so we get 3,956. There's my Earth's radius. How much is the radius of, we're going to add 200 on, so the radius of the satellite's going to be how much? 4156, right? Add 200 on there. We can barely see that. 4156. That's your radius of your satellite. Assuming the Earth's radius is at, how far does it travel if it revolves through an angle 10 radians? Okay. An angle of 10 radians. What are we going to do here? Yeah, we're not going to use it. We're going to think about this, yes? But school's up, time's out. So we're going to pick up here next class, okay? Does that make sense? Yes, sir. All right.